In this presentation, I will introduce and explain the nature of our vertical rocket launch experiment, and later on, I will describe our conclusions of the experiment. In this experiment, multiple facets of rocketry were explained using a Level 1 rocket kit alongside Newtonian mechanics and abstract calculus. The Tsiolkovsky ideal rocket equation, as well as the rocket equations for center of pressure and center of mass, were all used, all of which helped construct both an analytical model and an experimental approach. The center of mass, or gravity in the case of rockets, is the point of the rocket where the weight of it is distributed equally on all sides, whereas the center of pressure is the point where lift and drag act on the rocket. The main purpose of this experiment is to analyze the mechanisms of vertical rocket launching with a focus on rocket stability and calculations for its maximum height, otherwise known as the apogee. Both the Tsiolkovsky ideal rocket equation and the Berryman method were referenced in the calculations. The Berryman method, typically used as a basis for simulations, uses many equations to determine the center of pressure on a rocket, with four main assumptions. The angle of attack is near zero, the flow is steady and irrotational, the vehicle is a rigid body, and the nose tip is a sharp point. The center of mass was found by balancing the rocket on a string and finding its most balanced point. In the theoretical results, the center of pressure and mass were mathematically derived through equations involving calculus. The center of pressure was determined by using a cardboard replica of the rocket balanced on a string to find where its mass distribution was the most well distributed. The center of pressure must be more towards the bottom of the rocket than the center of mass in order to be considered stable. Stability is another very important aspect in rocketry. The caliber of stability can be found by dividing the distance between the 2 points over the diameter of the rocket's body.
This examination of vertical rocket launching explores the areas of center of mass and center of pressure. The center of mass is where the gravity acts on the rocket, and the center of pressure is where the aerodynamic forces, lift and drag, act on the rocket. The center of mass of a rocket is easily found through simple methods. However, the center of pressure is optimally found through the use of a wind tunnel, which was not available to use. The center of pressure can be approximated on a more rudimentary experiment. It is known that the caliber of stability, which involves the distance between the center of pressure and center of mass, is acceptable for a successful flight. The rocket used was built from a lock precision, high-tech kit to the standards of EEE Rocket Association for Level 1 certification. It is a high-powered rocket and used a Cicerone P38 2G white H110 motor and carried a small altimeter with negligible mass as the payload. The motor is ignited and allows a rocket to launch with a given thrust, and then there is a delay for when the rocket separates and the parachute is released. The parachute ought to be released after the apogee is reached, so that does not affect the height calculation. The rocket consists of a few major components, including the nose cone, payload bay, coupler, main airframe, rail rod, fins, and motor mount. All of these pieces were accounted for when calculating the dry mass of the rocket. There were some inconsistencies throughout the production of the rocket, which was built using epoxy and screws to hold everything together. These pieces are negligible for the mass. However, they are not necessarily symmetric on the rocket, and they may have affected the apogee and stability. Before launching the rocket, it was examined and approved by a EEE prefect as safe to fly. This is a video of it launching successfully for a Level 1 certification flight. In this experiment, the center of mass and center of pressure were approximately found using simple techniques. These experiments were based off of the basic principles of each point. First, the center of mass was found by tying a string into a slip knot and putting the rocket in it. The rocket was balanced at a certain point, which was found to be the center of mass. This is based on the principle that the mass is balanced at that found point. The center of mass was found to be 20.5 inches away from the motor retainer, which is the point of the rocket farthest back on the side of the fins. After that was found, experimental procedures were also used to find the center of pressure. First, a projection of the silhouette of the rocket was cut out onto a flat piece of cardboard. This was used because the center of pressure is approximately at the point where the surface area is balanced on either side. So a piece of cardboard or paper balanced at a point would show the center of pressure if the mass is negligible. The cardboard cutout was balanced on the same string, and the center of pressure was found to be 21.1 inches away from the motor retainer. This does not show stability, and that is because of the errors that are inherent in these simple experiments. First, the parachute was not able to be included, so that may have slightly affected the center of mass. Second, the cardboard cutout was not actually massless, and so the surface area was not the only measurement being balanced by the string. This experiment has been used historically and would often come up with these results. However, people would simply add clay to the nose cone because it would be better to be overly stable than not stable at all. To ensure stability, the center of pressure must be closer to the motor retainer than the center of mass, and adding weight to the front of the rocket at the nose cone would shift that center of mass, so that was the case. Another experiment done with this rocket was actually launching it earlier in the year under the guidance of the Tampa Tripoli Rocket Association. There, the center of pressure and center of mass are computed through a simulation, and while that is also an approximation, it did show that the center of pressure and center of mass for the rocket were in the correct order, and the fact that the rocket flew straight and successfully shows the stability caliber was acceptable. Apogee was also measured to be 2,754 feet, or 839.42 meters. Unfortunately, experiment results were not able to be replicated because of COVID-19, and there was no designated launch in March of 2020. However, if one were to launch this same rocket again, they may be able to use a video to track the rocket's movements and find a much more accurate location of center of pressure experimentally.
So I will be talking about the mathematical models for the flight analysis. First, we're gonna talk about the ideal rocket equation, since it's a very famous equation in rocketry, and we can't, of course, talk about rockets without this rocket equation. So I will briefly mention it. However, for our actual flight analysis to solve the issue at hand, we will not be using this equation for the reasons I will mention below. So to derive the rocket equation as Tsiolkovsky derived it, we're gonna use the simple and famous Newton's second law, F is equal to ma, which is also equal to m du dt, and m here is a function of time since we have fuel burning down and the mass is changing, and the udt is just the derivative of the velocity of the rocket. So we're gonna only consider thrust force in the ideal rocket equation because Tsiolkovsky himself ignored the drag and the gravitational force. So the only thing that's taken into account in this derivation is the thrust force and the mass as a function of time. And so we have a thrust force of a solid fuel rocket engine, which is dmdt ve delta pa. The mdt is the change in mass, or the slope of the mass function. Mass function is a linear plot, so we have a slope, a single slope. VE is the exhaust velocity, or the velocity at which the fuel is being rejected, or the velocity at which the fuel is leaving the rocket. And delta P is the pressure difference in the rocket engine, and A is the cross-sectional area of the rocket. By equating this thrust force is equal to mt du dt, and with some algebraic manipulation, we will get the final velocity after burnout equal to V equivalent ln m naught over mf, or ISP G is the gravitational acceleration, ln m naught over mf, and ln is just the natural log. V equivalent in this case is the exhaust velocity plus delta PA over m dot, and ISP is I over the weight, or V equivalent over G. So this way we have our ideal rocket equation. If you want to see the detailed derivation, it can be found in the reference below in our complete paper, because I will only talk about it shortly here. As I've mentioned earlier, we won't be using the ideal rocket equation to analyze our flight or calculate our apogee, because the ideal rocket equation, after doing some research, we figured that it's more fitted for larger rockets with higher fuel mass to rocket mass ratio. Sometimes the fuel mass can also be heavier than the rocket mass itself, in which the change in mass is not negligible. However, the rocket that we've used in this experiment is very small. It has a very little percentage of um, the fuel mass compared to the rocket. It was around 16% of the rocket mass. The fuel is around 16% of the rocket mass. And so we will assume that the mass is constant in this case. And we do this so that we are able to take into consideration the more important factors such as the drag force and the gravitational force, because those two forces play more important roles with smaller rockets than compared to bigger rockets. And those forces are ignored in the ideal rocket equation derivation. And when we use that equation, we got a really inaccurate apogee approximation. So we're gonna take those forces into consideration and assume constant mass instead. The thrust force is also assumed to be constant, as well as the air density. So again, we're gonna start with Newton's second law, but this time we have more than thrust force. We have m dv dt. dv dt is again the derivative of the velocity, and m this time is a constant, equal to t minus mg minus kv squared, where t is the thrust force, mg is the gravitational force, and kv squared is the drag force. And as you can see in the diagram, it's all the positive direction for v and y are all pointing up. Again, with algebraic manipulation and integration with separation of variables, we will be able to get the velocity as a function of time. And we have a few denotations such as q and x. Those are just for the simplification of writing. We don't want to write everything all over again, so we denoted it. And the detailed derivation once again can be found in the reference section. So we wanted to find the velocity, and I'm not sure if I mentioned it earlier, but this velocity is for the boost phase. Boost phase means when the fuel is still burning out, when there's still thrust. And so we found this velocity as a function of time because we'll need it in our apogee calculation. And what we're interested in is the burnout velocity, which we can find by simply plugging t with the burnout time. Burnout time can be found in the specifications of the rocket engine when you purchase it. So if you plug in the burnout time, you'll get burnout velocity. And so we're gonna go to now the boost phase, and we're gonna think about the altitude at burnout. So before we derive the burnout velocity, now we're gonna derive the burnout altitude. Again, we can use the same equation. However, we're gonna use a trick. Instead of t minus mg minus kv squared is equal to m dv dt, we're gonna times by dy over dy, which is just 1, so it won't change the equation in any way. But now we get dv over dy and dy over dt. So dy over dt is just v itself. So now we only have dv and dy, and v and y as variables. And so now we can again do separation of variables and integrate.
And then we'll get y as a function of v, which is y is equal to m over 2k ln q squared minus v squared over q, and q is the same q as previously. Once we derive the altitude at burnout, now we're gonna talk about the coast phase. The coast phase is after the fuel burned out, and so there's no thrust force anymore, but the rocket is still going up because it still has momentum, upward momentum, and so it'll only stop going up when the momentum gets canceled, when the other forces like the drag force and the gravitational force cancel all the motion of the rocket upwards. And so now we're gonna have two forces instead of three. We're not gonna have thrust anymore because the fuel already burned out. So we're gonna have negative mg minus kv squared is equal to mdv. And again, we're gonna use the same trick. So it's mdv dy dt. And again, with separation of variables, integration, you'll get y as a function of v, which is m2k ln mg plus kv squared over mg. This v here will be the burned out velocity because that's our initial v. If you look at the detailed derivation, you'll understand why v is the initial v, and this initial v is the burnout. Well, this is from the burnout time, so it's burnout velocity. And now, if you find all the constants, the average mass, by the way, we also have a special way of calculating average mass to minimize the error. You can find that in our paper. So after doing all the simple calculations to get all the constants, we'll get the burnout altitude to be 237.46 meters and the coasting altitude to be 592.35 meters. So when you add them together, you get the apogee, which is 829.81 meters. The experimental results is 839.42 meters, which give us a percent error of 1.14%. And so you can see that this percent error is very small. It means that our model is pretty reliable, pretty accurate, that the assumptions that we made did not affect the calculations, or the assumptions that we made did not give that much error. And so to minimize this error, or to confirm further that our model is accurate, it's ideal that you do many experiments, launch the rocket multiple times to see, to get the average error, to see if the results are consistent. However, due to the current crisis, the COVID-19 crisis, we were not able to do multiple launches. There was only one launch done since the launching site is shut. But for future projects, it's recommended that you do multiple launches. And finally, this is just the height as a function of time. Earlier, we derived the boost phase altitude as a function of velocity, but if we plug in the velocity as a function of time, which we also derived into the altitude as a function of velocity, we can plot the altitude as a function of time, which gives us the plot that you can see. And this is only the boost phase, not the coast phase.
The main sources of error of the experimental results were determined as being a lack of payload during the center of mass experiment and a significant level of discrepancies with the cardboard replica of the rocket throughout the center of pressure experiment. This method used in the experimental approach was not accurate because it assumes the rocket is flying sideways while moving upwards, so the direction it is moving is perpendicular to where it is facing, which causes an overstability because it makes the center of pressure seem too far forward. This method makes sure the rocket flies safely and more stable. However, one would often have to add mass to the nose cone area to ensure the center of mass is more towards the front than the center of pressure. An alternate experiment to potentially improve these center of pressure errors could be done by using a wind tunnel in order to more accurately measure a rocket's center of pressure. In this experiment, the apogee and stability of a vertical launching rocket were explored and calculated with respect to the center of gravity and pressure using equations derived from Newton's second law and Tsiolkovsky's ideal rocket equation. The center of mass and center of pressure are crucial to measure because they must be in the correct order with an acceptable caliber stability between them for the rocket to fly straight. The rocket's stability in flight strongly affects apogee because if it is not flying straight, it is less aerodynamic and consequently does not reach as high as it could have otherwise. The experiment aimed to compare the theoretical and experimental results of the stability and apogee of a slender level 1 vertical launching rocket, which found that the burnout speed was calculated to be 199.45 meters per second, with an apogee of 829.81 meters, while the experiment measured an apogee of 839.42 meters. The experimental results showed that the distance between the centers of mass and pressure had a 0.6-inch disparity, which shows the rocket's instability. In comparing the theoretical and experimental results for the apogee, it was found that there was a 1.14% error between the measurements and calculations.